So I'm going to go ahead and read some of Albert Einstein's Relativity. So it comes from this book, page 227, What is the Theory of Relativity? Written at the request of the London Times, published November 28th, 1919. So relativity's been around for quite some time, huh? Is relativity a myth, too? So I'm just going to read this so that way I can listen to it and understand it more. I don't totally understand it, so I'm just going to read it straight through, and we'll see if that accomplishes something. So just 30 minutes of straight reading. But it's Albert Einstein, right? I gladly accede to the request of your colleague to write something for the Times on relativity. After the lamentable breakdown of the old active intercourse between men of learning, I welcome this opportunity of expressing my feelings of joy and gratitude toward the astronomers and physicists of England. It is thoroughly in keeping with the great and proud traditions of scientific work in your country that eminent scientists should have spent much time and trouble, and your scientific institutions have spared no expense to test the implications of a theory which was perfected and published during the war in the land of your enemies. Though the investigation of the influence of the gravitational field of the sun on light rays is a purely objective matter, I cannot forbear to express my personal thanks to my English colleagues for their work, for without it, I could hardly have lived to see the most important implication of my theory tested. We can distinguish various kinds of theories in physics. Most of them are constructive. They attempt to build up a picture of the more complex phenomena out of the materials of a relatively simple formal scheme from which they start out. Thus, the kinetic theory of gases seeks to reduce mechanical, thermal, and diffusional processes to movements of molecules, i.e., to build them up out of the hypothesis of molecular motion. When we say that we have succeeded in understanding a group of natural processes, we invariably mean that a constructive theory has been found which covers the processes in question. Along with this most important class of theories, there exists a second, which I call principal theories. These employ the analytic, not the synthetic method. The elements which form their basis and starting point are not hypothetically constructed, but empirically discovered ones. General characteristics of natural processes, principles that give rise to mathematically formulated criteria which the separate processes or the theoretical representations of them have to satisfy. Thus, the science of thermodynamics seeks by analytical means to deduce necessary conditions which separate events have to satisfy from the universally experienced fact that perpetual motion is impossible. The advantages of the constructive theory are completeness, adaptability, and clearness. Those of the principal theory are logical perfection and security of the foundations. The theory of relativity belongs to the latter class. In order to grasp its nature, one needs first of all to become acquainted with the principles on which it is based. Before I go into these, however, I must observe that the theory of relativity resembles a building consisting of two separate stories, the special theory and the general theory. The special theory on which the general theory rests applies to all physical phenomena with the exception of gravitation. The general theory provides the law of gravitation and its relations to the other forces of nature. It has, of course, been known since the days of the ancient Greeks that in order to describe the movement of a body, a second body is needed to which the movement of the first is referred. The movement of a vehicle is considered in reference to the Earth's surface, that of a planet to the totality of the visible fixed stars. In physics, the body to which events are spatially referred is called the coordinate system. The laws of the mechanics of Galileo and Newton, for instance, can only be formulated with the aid of a coordinate system. The state of motion of the coordinate system may not, however, be arbitrarily chosen if the laws of mechanics are to be valid. It must be free from rotation and acceleration. A coordinate system which is admitted in mechanics is called an inertial system. The state of motion of an inertial system is, according to the mechanics, not one that is determined uniquely by nature. On the contrary, the following definition holds good. A coordinate system that is moved uniformly and in a straight line relative to an inertial system is likewise an inertial system. By the special principle of relativity is meant the generalization of this definition to include any natural event whatever. Thus, every universal law of nature which is valid in relation to a coordinate system C must also be valid as it stands in relation to a coordinate system C1, which is in uniform translatory motion relatively to C. Let me say that again. So there's C, and then there's C with a little notch on the right above it. So C and C1, two different letters that represent different values. By the special principle of relativity is meant the generalization of this definition to include any natural event whatever. Thus, every universal law of nature which is valid in relation to a coordinate system C must also be valid as it stands in relation to a coordinate system C1, which is in uniform translatory motion relatively to C. The second principle on which the special theory of relativity rests is the principle of the constant velocity of light in vacuo. This principle asserts that light in vacuo always has a definite velocity of propagation, independent of the state of motion of the observer or of the source of light. The confidence which physicists place in this principle springs from the successes achieved by the electrodynamics of Maxwell and Lorentz. Both the above-mentioned principles are powerfully supported by experience, but appear not to be logically reconcilable. The special theory of relativity finally succeeded in reconciling them logically by a modification of kinematics, i.e., the doctrine of the laws relating to space and time, from the point of view of physics. It became clear that to speak of the simultaneity of two events had no meaning except in relation to a given coordinate system, and that the shape of measuring devices and the speed at which clocks move depend on their state of motion with respect to the coordinate system. But the old physics, including the laws of motion of Galileo and Newton, did not fit in with the suggested relativist kinematics. From the latter, general mathematical conditions issued to which natural laws had to conform if the above-mentioned two principles were really to apply. To these, physics had to be adapted. In particular, scientists arrived at a new law of motion for rapidly moving mass points, which was admirably confirmed in the case of electrically charged particles. The most important upshot of the special theory of relativity concerned the inert masses of corporeal systems. It turned out that the inertia of a system necessarily depends on its energy content, and this led straight to the notion that inert mass is simply latent energy. The principle of the conservation of mass lost its independence and became fused with that of the conservation of energy. The principle of conservation of mass lost its independence and became fused with that of the conservation of energy. Thus, the special theory of relativity, which was simply a systematic development of the electrodynamics of Maxwell and Lorentz, pointed beyond itself, however. Should the independence of physical laws of the state of motion of the coordinate system be restricted to the uniform translatory motion of coordinate systems in respect to each other? What has nature to do with our coordinate systems and their state of motion? If it is necessary for the purpose of describing nature to make use of a coordinate system arbitrarily introduced by us, then the choice of its state of motion ought to be subject to no restriction. The laws ought to be entirely independent of this choice, general principle of relativity. The establishment of this general principle of relativity is made easier by a fact of experience that has long been known, namely that the weight and the inertia of a body are controlled by the same constant, equality of inertial and gravitational mass. Imagine a coordinate system which is rotating uniformly with respect to an inertial system in the Newtonian manner. The centrifugal forces which manifest themselves in relation to the system must, according to Newton's teaching, be regarded as effects of inertia. But these centrifugal forces are, exactly like the forces of gravity, proportional to the masses of the bodies. Ought it not be possible in this case to regard the coordinate system as stationary and the centrifugal forces as gravitational forces? This seems the obvious view, but classical mechanics forbid it. This hasty consideration suggests that a general theory of relativity must supply the laws of gravitation, and the consistent following up of the idea has justified our hopes. But the excuse me. Wow, okay, so 20 more minutes to go. This hasty consideration suggests that a general theory of relativity must supply the laws of gravitation, and the consistent following up of the idea has justified our hopes, but the path was thornier than one might suppose because it demanded the abandonment of Euclidean geometry. This is to say, the laws according to which solid bodies may be arranged in space do not completely accord with the spatial laws attributed to bodies by Euclidean geometry. This is what we mean when we talk of the curvature of space. The fundamental concepts of the straight line, the plane, etc., thereby lose their precise significance in physics. The general theory of relativity, the doctrine of space and time, or kinematics, no longer figures as a fundamental independent of the rest of physics. The geometrical behavior of bodies and the motion of clocks rather depend on gravitational fields, which in their turn are produced by matter. The new theory of gravitation diverges considerably as regards principles from the new theory of gravitation diverges considerably as regards principles from Newton's theory, but its practical results agree so nearly with those of Newton's theory that it is difficult to find criteria for distinguishing them which are accessible to experience. Such have been discovered so far. Number one, in the revolution of the eclipses of the planetary orbits around the sun, confirmed in the case of Mercury. Number two, in the curving of light rays by the action of gravitational fields, confirmed by the English photographs of eclipses. Number three, in a displacement of these spectral lines toward the red end of the spectrum in the case of light, transmitted to us from the stars of considerable magnitude. And that's unconfirmed so far, but it has since been confirmed since he wrote this. The chief attraction of the theory lies in its logical completeness. If a single one of the conclusions drawn from it proves wrong, it must be given up. To modify it without destroying the whole structure seems to be impossible. Let no one suppose, however, that the mighty work of Newton can really be superseded by this or any other theory. His great and lucid ideas will retain their unique significance for all time as the foundation of our whole modern conceptual structure in the sphere of natural philosophy. Note, some of the statements in your paper concerning my life and person owe their origin to the lively imagination of the writer. Here is yet another application of the principle of relativity for the delectation of the reader. Today I am described in Germany as a German savant and in England as a Swiss Jew. Should it ever be my fate to be represented as a bête noire, I should, on the contrary, become a Swiss Jew for the Germans and a German savant for the English. So there you go. That's relativity. So let's read some more. So this comes from the page 249. No. This comes from the page of 285. Notes on the origin of the general theory of relativity, 1934. So this one was written 1919, and then this one was spoken 1934. Okay, so what, 15 years later? I gladly accede to the request that I should say something about the history of my own scientific work. Not that I have an exaggerated notion of the importance of my own efforts, but to write the history of other men's work demands a degree of absorption in other people's ideas, which is much more in the line of the trained historian. To throw light on one's own earlier thinking appears incomparably easier. Here, one has an immense advantage over everybody else, and one ought not to leave the opportunity unused out of modesty. When, by the special theory of relativity, I had arrived at the equivalence of all so-called inertial systems for the formulation of natural laws, 1905, the question whether there was not a further equivalence of coordinate systems followed naturally, to say the least of it. To put it in another way, if only a relative meaning can be attached to the concept of velocity, ought we nevertheless to persevere in treating acceleration as an absolute concept? From the purely kinematic point of view, there is no doubt about the relativity of all motions whatever, but physically speaking, the inertial system seemed to occupy a privileged position which made the use of coordinate systems moving in other ways appear artificial. I was, of course, acquainted with Mach's view, according to which it appeared conceivable that what inertial resistance counteracts is not acceleration as such, but acceleration with respect to the masses of the other bodies existing in the world. There is something fascinating about this idea to me, but it provided no workable basis for a new theory. I came first a step nearer to the solution of the problem when I attempted to deal with the law of gravity within the framework of the special theory of relativity. Like most writers at the time, I tried to frame a field law for gravitation, since it was no longer possible, at least in any natural way, to introduce direct action at a distance owing to the abolition of the notion of absolute simultaneity. The simple thing was, of course, to retain the Laplacian scalar potential of gravity and to complete the equation of Poisson, Poisson, in an obvious way by a term differentiated with respect to time in such a way that the special theory of relativity was satisfied. The law of motion of the mass point in a gravitational field had also to be adapted to the special theory of relativity. The path was not so unmistakably marked out here, since the inert mass of a body might depend on the gravitational potential. In fact, this was to be expected on account of the principle of the inertia of energy. These investigations, however, led to a result which raised my strong suspicions. According to classical mechanics, the vertical acceleration of a body in the vertical gravitational field is independent of the horizontal component of its velocity. Hence, in such a gravitational field, the vertical acceleration of a mechanical system or of its center of gravity works out independently of its internal kinetic energy. But in the theory I advanced, the acceleration of a falling body was not independent of its horizontal velocity or the internal energy of a system. This did not fit in with the old experimental fact that all bodies have the same acceleration in a gravitational field. This law, which may also be formulated as the law of the equality of inertial and gravitational mass, was now brought home to me in all its significance. I was in the highest degree amazed at its existence and guessed that in it must lie the key to a deeper understanding of inertia and gravitation. I had no serious doubts about its strict validity, even without knowing the results of the admirable experiments of Eötvös, E-O-T-V-O-S, with umlaut over both the O's, Eötvös, which, if my memory is right, I only came to know later. I now abandon as inadequate the attempt to treat the problem of gravitation in the manner outlined above within the framework of the special theory of relativity. It clearly failed to do justice to the most fundamental property of gravitation. The principle of the equality of inertial and gravitational mass could now be formulated quite clearly as follows. In a homogeneous gravitational field, all motions take place in the same way as in the absence of a gravitational field in relation to a uniformly accelerated coordinate system. If this principle held good for any events whatever, the principle of equivalence, this was an indication that the principle of relativity needed to be extended to coordinate systems in non-uniform motion with respect to each other if we were to reach a natural theory of the gravitational fields. Such reflections kept me busy from 1908 to 1911, and I attempted to draw special conclusions from them, of which I did not propose to speak here. For the moment, the one important thing was the discovery that a reasonable theory of gravitation could only be hoped for from an extension of the principle of relativity. What was needed, therefore, was to frame a theory whose equations kept their form in the case of nonlinear transformations of the coordinates. Whether this was to apply to arbitrary, continuous transformations of coordinates or to only certain ones, I could not for the moment say. 9 more minutes, okay. I soon saw that the inclusion of nonlinear transformations as the principle of equivalence demanded was inevitably fatal to the simple physical interpretation of the coordinates, i.e., that it could no longer be required that coordinate differences could signify direct results of measurement with ideal scales or clocks. I was much bothered by this piece of knowledge, for it took me a long time to see what coordinates at all meant in physics. I did not find the way out of this dilemma until 1912, and then it came to me as a result of the following consideration. A new formulation of the law of inertia had to be found, which in the case of the absence of a real gravitational field passed over into Galileo's formulation for the principle of inertia if an inertial system was used as a coordinate system. Galileo's formulation amounts to this. A material point which is acted on by no force will be represented in four-dimensional space by a straight line, that is to say, by a shortest line, or more correctly, an extremal line. Extremal. This concept presupposes that of the length of a line element, that is to say, a metric. In the special theory of relativity, as Minkowski had shown, this metric was a quasi-Euclidean one, i.e. the square of the length ds of a line element was a certain quadratic function of the differentials of the coordinates. If other coordinates were introduced by means of a nonlinear transformation, ds squared remains a homogeneous function of the differentials of the coordinates, but the coefficients of this function, g, and it looks like a little u and v, a weird little u with a little thing next to it, so GUV, cease to be constant and become certain functions of the coordinates. In mathematical terms, this means that physical four-dimensional space has a Riemannian metric, Riemannian. The time-like extremal lines of this metric furnish the law of motion of a material point which is acted on by no force apart from the forces of gravity. The coefficients, GUV, of this metric at the same time describe the gravitational field with reference to the coordinate system selected. A natural formulation of the principle of equivalence had thus been found, the extension to which any gravitational field would ever formed a perfectly natural hypothesis. The solution of the above-mentioned dilemma was therefore as follows. A physical significance attaches not to the differentials of the coordinates, but only to the Riemannian metric corresponding to them. A workable basis had now been found for the general theory of relativity. Two further problems remain to be solved, however. Number one, if a field law is expressed in terms of the special theory of relativity, how can it be transferred to the case of a Riemannian metric? And two, what are the differential laws which determine the Riemannian metric, i.e. GUV itself? I worked on these problems from 1912 to 1914 together with my friend Grossman. We found that the mathematical methods for solving problems, one, lay ready in our hands in the absolute differential calculus of Ricci, R-I-C-C-I, and Levi Civita, C-I-V-I-T-A. As for the problem 2, its solution obviously required the construction from the GUV of the differential invariance of the second order. We soon saw that these had already been established by Riemann, the tensor of curvature. We had already considered the right field equation for gravitation 2 years before the publication of the general theory of relativity, but we were unable to see how they could be used in physics. On the contrary, I felt sure that they could not do justice to experience. Moreover, I believed that I could show on general consideration that a law of gravitation invariant with respect to arbitrary transformations of coordinates was inconsistent with the principle of causality. Causality. There were errors of thought which cost me 2 years of excessively hard work, until I recognized them as such at the end of 1915, and after having ruefully returned to the Riemannian curvature, succeeded in linking the theory with the facts of astronomical experience. In the light of knowledge attained, the happy achievement seems almost a matter of course, and any intelligent student can grasp it without too much trouble. But the years of anxious searching in the dark, with their intense longing, their alternations of confidence and exhaustion, and the final emergence into the light, only those who have experienced it can understand that. So there you go. That's the history of how he came to the conclusion of relativity. Now the physics and reality.